All right, guys, before we get started, are there any questions over the homework? Last thing we're looking at in chapter 1 is inverse functions. So finding the inverse using graphs, horizontal line test, determine if functions are inverse or to find an inverse. So we know that ordered pairs can represent a function. For instance, the function x plus 4, f of x equals x plus 4 from the set of 1, 2, 3, 4 to the set 5, 6, 7, 8. So for us here, when we plug 1 in for x, we get a y value of 5. We plug 2 in for x, we get a y value of 6, 3, 7, 4, 8. In this case, by interchanging the first and second coordinates of each function, we get its inverse, denoted by f inverse of x, f to the negative 1. So the inverse, we end up flipping them. So if we're told 1, 5, its inverse is going to be 5, 1, 6, 2, 7, 3, 8, 4. So when we're given an ordered pair, or sets of ordered pairs, all we got to do is flip the x and y. The domain becomes the range becomes the domain with the inverse. And that's all it's signifying this here, that x minus 4 is its inverse for x plus 4. So x plus 4 takes a value in the x, our domain, and maps it to the range value. And the inverse takes that y value and brings it back to the corresponding x. It goes from one to the other as an undoing effect. So in other words, when you use or do a composition of the inverse and a function, you obtain the identity function. So what that means for us here, so if we plug the function in, f of x minus 4, f of the inverse, we get x minus 4 plus 4. And we drop the parentheses. Our negative 4 plus 4 is 0, telling us that f of f inverse of x is just x. They are indeed inverses. If we do this the other way, we plug f of x in first, we'll get f inverse of x plus 4. Which will tell us that we have x plus 4 minus 4, which is also x. Because f of f inverse of x will equal f inverse of f of x, which will all equal just x. Because if we take the composite of two functions and we get x, exactly x, nothing else, it can't be 2x, 3x, it has to be just x, it tells us that those two functions are indeed inverses. And this isn't anything new. We've done this before. We talked about this before in Algebra 2. Find the inverse of 4x and then verify. So if we're finding the inverse of 4x, the main way we went about finding this was first replacing f inverse with, or f of x with y. Y equals, replace f of x with y. Our second step is to switch the x and y. Replace f of x with y, flipped x and y. Now we're going to solve for y. And to do that, we're going to divide both sides by 4, telling us y is equal to x over 4. And lastly, we replace f inverse, or y with f inverse, because this is the inverse function. Questions on this here? I think we somehow, or somewhat remember doing these, yes? So, To undo this function, you need to divide instead of multiply, giving us this here. Now we can check and make sure and verify that they are indeed inverses. So we have our f of f inverse of x. So we plug the f inverse in, which is our x over 4. Then we replace every x in f of x with it, telling us that we have 4 times x over 4, which is just x. We can do the same thing with f inverse of f of x. Replace f of x, so 4x, in there, giving us 4x over 4, which is just x. Questions on any of this here so far? Now we'll go back over why, because x squared, our quadratic functions aren't actually, they don't have an inverse function. They do have an inverse, they're just not a function. So we have to restrict the domain for it to work. Now, we're going to find the inverse of x squared plus 2. So the first thing we're going to do is replace f of x with y. Then our second step is to switch
May I have your attention? May I have your
x
attention,
and y.
please? Any senior who is playing basketball, track, or powerlifting needs to come by the office at their convenience and pick up a form for senior night and turn it back in to me before this Thursday. Thank you.
Now we're going to solve for y. We're going to get y by itself. So the first thing we'll do is subtract 2 from both sides, telling us y squared is equal to x minus 2. Last thing we're going to do is take square root of both sides. Square root of y squared is y is equal to plus or minus the square root of x minus 2. Now, before we replace it with f inverse of x, there is one last thing we're going to need to do with this here. Because, and I'm going to graph it here to kind of make the point. What was the way that we tested to make sure an equation is a function? It has to pass the what? Because we had a test for checking if an equation is a function or if a graph's a function. It had to pass the or the vertical line test, yes? Because if we draw a vertical line and it crosses the graph in more than one place, it's not a function. It is an equation, it's just not a function. Because here we have x minus 2, and we had negative with our square root of x minus 2. Because we're saying that the equation is positive or negative the square root of x minus 2, yes? This is what we have. Now it is in 2 different colors, just because of how the calculator is set up here. Blue. That is all one function. Is that a function? No, because it doesn't pass the vertical line test. So really with this here, this is not a function. So really it doesn't, x squared plus 2 doesn't have an inverse as a function itself. So we put a restriction on it. So we're saying for when x is greater than 2, greater than or equal to 0. All the values for x when it's greater than 0. So all this is saying our domain. The x values that we have to be what? Greater than or equal to 0. And this x squared, our f of x, is going to map it to the range values. And our range values are our y values. Well, we're going to go down to x squared plus 2. Graph. So the graph in black is our normal equation, yes? Now let's look at the y values. So for us here, 0 has the smallest y value of 2, which means all the y values for this function here are going to be greater than or equal to 2. Okay? We can kind of see that on the graph more than we can just... All this is saying that when x is 0, we get the smallest y value of 2. X is going to get bigger than that. It can also be negative, but here we said that we're only looking at the positive. And even all the positive values, it starts at 0 and goes up. The inverse function is going to go back the other way, f inverse of x. So the input values, the values we're plugging into the function, have to be greater than or equal to 2 or bigger, yes? Because the y values now are greater than or equal to 0. They're positive. If we look at this here, well, both of these, the first value we actually get out of the other function is at 2. We get 0. That is what it's telling us. And we're told that it wants all the values greater than 0. Well, that one's giving me the negative. So really, we're just looking at that first quadrant. And all that is to say, because we restricted it on the positive x values, this is not going to be negative. We're just looking at f inverse of x for the positive square root of x minus 2. So quadratics do have an inverse equation, they just do not have an inverse function on the entire set. We have to restrict the values to get the function. Otherwise, it doesn't have one. Questions on this here? It's a long explanation to say that we don't have the negative. Now, the other part it asks for us to do here is to verify. Now, to verify, we're going to take f of f inverse of x. Now, our f inverse of x we found as the square root of x minus 2. So we're going to find f of f inverse of x, our composite function. So the first one we get is f inverse of x. We plug it in. Now we're going to plug the square root of x minus 2 into every x in f of x, which is really just going to be the square root of x minus 2 squared plus 2. Now most of these here, especially depending on the function, can get very complicated very quick, but they simplify themselves down very quickly, especially when they are inverses. So the first thing we can see here is that we have the square root squared. Well, the square root and the square would cancel, telling us that we have x minus 2 plus 2. Well, negative 2 plus 2 is 0, leaving us with x. Telling us that f of f inverse of x is x. So now we're going to look at f inverse of f of x. Well, f of x is our x squared plus 2. Now for this one here, we're going to replace every x in f inverse of x with x squared plus 2. So we have the square root of the quantity x squared plus 2 minus 2. We'll drop the parentheses, and our plus 2 minus 2 become what? 0. Telling us that we have the square root of x squared, which is verifying that f of f inverse of x is equal to f inverse of f of x, which is x. Because as long as f inverse of f of x and f inverse of f of x, try that one more time. F of f inverse of x is equal to f inverse of f of x, which are both equal to x, means that these two are indeed inverses. So that's how we would just verify. Questions on this here? So definition of an inverse, f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of x. Under these conditions, the function g is an inverse of the function f, and we can denote them as inverses. Do not be confused with the -1. It's not f to the negative first power, it's f inverse, or the reciprocal. It's not the reciprocal. So if we wanted to verify that these two functions are inverses, all we have to do is find the composite of f of g of x and verify that this does equal x. In doing so, the first thing we're going to do is replace g of x with its function. 5 over x plus 2. We just replace g of x with what it's equal to. Now here we're going to replace every x in f of x with this entire expression, 5 over x plus 2. So what that will give us is 5 over x plus 2 minus 2. Questions on how we got to this here? Nothing in front of the parentheses, so we can go on and just combine these. 2 minus 2 is telling us that we have 5 over x. 5 over x. So really what we're saying is that we have 5 divided by 5 over x. We changed the multiplication, so we're saying that we have 5 times x over 5. 5 over 5 would cancel, telling us that it is indeed x. G of f of x. Just like with the previous one, we'll replace f of x with its function, 5 over x minus 2. Now we're going to plug that into every x in g of x. So we'll have 5 over x minus 2 plus 2. Now the first thing we're going to have to simplify is the 5 over x minus 2. Really what we're saying is that we have 5 divided by 5 over x minus 2 plus 2. We don't really need the parentheses, but it's just reminding ourselves we're going to have to deal with that division first. And to divide two fractions, we change it from division to multiplication and flip. But again, our 5 and 5 would cancel, telling us that we have x minus 2 plus 2, which is just x. Because again, to show that these two are indeed inverses, we need f of g of x and g of f of x to both equal x. And when we can show that they do both equal x, we have verified that they are indeed inverses. Questions on this here? Yes, there's a lot of steps to show that these are inverses. Graphs. The graph of a function and its inverse are related to each other in the following way. If the point A, B lies on the graph, then the point B, A must lie on its inverse. This means that the graph f inverse of x is a reflection of the graph of f in the line y equals x. So a function and its inverse will always reflect across this line y equals x. So we've already said that these two are inverses of each other. I'll put this back. Of this here. So if we type, we'll get a fifth equation, the fourth equation, x, we can see that that graph is reflected across this line y equals x. So we can take any of them and show that they are indeed a reflection across this line. 1-to-1. The reflection property of the graph of inverse gives you a geometric test for determining whether a function has an inverse. This test is called the horizontal line test for inverse functions. So if we can draw a horizontal line and it crosses the original graph from more than one place, it does not have an inverse, or its inverse is not a function. A function f has an inverse if and only if it has no horizontal line intersecting the graph of f in more than one place. And it's a test for inverse function. It doesn't mean that there's not an equation for the inverse, it's just not a function. So if no horizontal line intersects the graph at more than one point, then no y value is matched with more than one x value. It's 1-to-1, so we can call it a function. Consider the table. The table on the right is the same as the table on the left. So we get this here. So this is its inverse. So the left is the function itself. And what they're bringing attention to is this here. Because when we find its inverse, we switch those x's and y's. We get this here. This is inverse doesn't pass the vertical line test. So it's not a function. So if the original function does not pass the horizontal line test, we can draw a line horizontally and cross it in more than one point. -2, 4, 2, 4. Its inverse is not a function because its inverse will not pass the vertical line test of being at 4, -2, 4, 2, 4, -2. Because it's going to cross the same spot more than one point. We can still have an equation for the inverse, it's just not going to be a function. The table on the right does not represent a function because the input 4, for instance, matches with two different outputs. So we have this graph shown here. There's no way we can draw a horizontal line and it crosses more than one point. Therefore, it is 1-to-1 and does have an inverse function. Here, we can draw a horizontal line that intersects the graph of f at more than one point. F is not 1-to-1 and does not have an inverse function. It can have an inverse, it's just not going to be a function. All right. Questions on this so far? Let's look at this here. F of x equals 5 minus 3x over 2. So when we find this inverse, first thing we're going to do is replace f of x with y. Now we're going to switch x and y. Now we're going to solve it for y. So we rewrite f of x as y, switch x and y, solve for y. Now with any of the rational equations, the first thing we're always going to want to do is get rid of the bottom of the fraction. We're going to multiply both sides by the bottom of this fraction. So here it's 2. Because here our 2 and 2 will cancel, telling us that 2x is equal to 5 minus 3y. What can we do next? Because we're wanting to get y by itself. We can subtract 5. Telling us that negative 3y is equal to 2x minus 5. Then we would divide by negative 3. And lastly, replace y with x inverse of x. Now, we don't necessarily have to leave that negative in the bottom of the fraction. We can pull it and put it out front. Say that we have negative 2x minus 5 over 3. Or we can distribute it across the top, which means we still have a positive 3 on bottom, but our 2x on top is going to become negative, and the 5 is going to be positive. So there is more than one way to write this. Questions on this here? So we have the graph, and a lot of these here, I'd graph them, see if we do have an inverse. This one does. There's not going to be a line that we can draw. Okay, those are two different graphs. Yep. And we'll talk about that in a little bit, but we don't have a line, and it does work. Questions on this so far? We'll look at another one. F of x equals the square root of 2x minus 3. Now, the first thing we're going to do is replace f of x with y. Replace f of x with y. Then we're going to switch the x and y. Then we're going to solve for y. Now, the first thing we'll need to do is get rid of that radical. So we're going to square both sides. Because over here, the square root and square will cancel, leaving us with 2y minus 3 is equal to x squared. What can we do next? We'd add 3 to both sides. Telling us that 2y is equal to x squared plus 3. And lastly, both sides by 2, telling us y is equal to x squared plus 3 over 2. And we'll replace our y with f inverse of x. So, questions on this so far? Now, we do have to put some restrictions on this here, because again, the function is taking the domain to a set range for f of x. And the range is going, and our inverse is taking the range back to the corresponding domain. Now, for us here, the square root of 2x minus 3, for even roots, what's inside the radical cannot be negative. So what that means for us is that 2x minus 3 has to be greater than or equal to 0. And if we solve this here, x has to be greater than or equal to 3/2. So our domain value is going to be greater than or equal to 3/2. 3/2, the y value is going to be 0, which means the range values have to be greater than or equal to 0, the corresponding y value. And the way that I find this, and all we got to do is plug the smallest value in. So we have the square root of 2 times 3/2 minus 3. 2 times 3/2 is 3. 3 minus 3 is 0. Square root of 0 is 0. Now, it's not always going to be the case where it is. The range is going to be 0, greater than or equal to 0. Because we've had one already where the range was greater than or equal to 2. So it can be higher, it can be lower. We just have to plug it in to find it. Now, the reason I point this out is because our inverse function that we had, its x values are now greater than or equal to 0, and its range values are greater than or equal to 3/2. So all that means for us down here at the bottom is that for our inverse, the x values have to be greater than or equal to 0. I'm not going to be so much of a stickler on making sure that you put that restriction, but I do want you to be aware of it. So, questions on that there? That's it. That's the end of that chapter.